In this video, I'm going to be making a programmable delay with one of these little Arduinos. They're super cheap, and so that makes it a really interesting way to get this done. I'm going to be going over a lot of stuff in this video, even though some might say like, oh, doing a delay is really easy. It's only easy if you've done it a couple thousand times. There's a lot of places where a person might get led astray doing one of these things if they've never programmed before, especially. So I'm going to cover as many of those places as possible in this video. And at the end of the video, I'm going to be connecting up one of these little relay boards because it's a good instructional way to show that we can control signals. So first things first, when you get one of these Arduinos and you plug it into the USB, you should notice one of the lights flashing. If you don't notice one of the lights flashing, that doesn't necessarily mean yours is broken. But this light's flashing just because there's a lot of these are programmed from the factory to flash. And the first thing I'm going to do is open up the Arduino IDE, and we're going to see if we can program this device. When the Arduino IDE opens up, it usually comes up with a blank program. And if we go to upload, it's going to try and program the device that we're connected to. So as you can see, when I programmed it just with that blank program, there's now no more flashing. So this flashing, it was just a program. It's not like it's broken now or anything. If you go to program the board and start getting error messages, there's two places to check. One is under Tools. Make sure you've got the port selected correctly. So for instance, this one is selected on TTYS0. I'm connected to USB 0, so I'm going to select that instead. Another thing to make sure of is that you've got the correct Arduino device selected. So you can see down in the bottom, this says I'm trying to program an Arduino Leonardo, but that's not what I have. And there are some times when you can have this wrong and still get it to at least try to program. That's also selected under the Tools menu. Just go into the board, menu, and select the Arduino device that you're using. I'm using the Nano. The next question is, can we actually turn that LED on and off with our code? Now I know, since I've been programming on the Arduino Nano before, that little LED device is on pin 13, pin D13. So what I'm going to do in the loop section of the code is do a digital write, and then I'm going to say put pin 13 to high. And high is going to be in all caps. It's going to turn blue. If it's not in all caps, it's not going to turn blue. And when we go to compile and upload it, it's going to think that this is a special variable. It's not going to really know it's a keyword. So when we program it, here's what happens. We get a really faint oh, that's horrible. In the close-up, we can see the LED is glowing really faintly. The reason for that is the pin was never set up as an output. On the Arduino, when a pin is configured as an input, writing a high to it is going to enable a pull-up resistor. A pull-up resistor is a resistor that's connected between a pin and a voltage rail. A pull-up resistor is connected to the high voltage rail. A pull-down resistor is connected to the low voltage rail. One of the advantages to having a pull-up resistor is that it reduces the number of parts you need when you're connecting things to the microcontroller. Here's an example. We've got a switch connected to an input of a microcontroller. When the switch is closed like it is in this picture, that microcontroller sees a low signal because the switch is connecting that input pin to ground. But in this situation, when that switch is open, the pin to the microcontroller is left floating, and there's no really good way to predict what it's going to read as. By adding a pull-up resistor to 5 volts, that pin is no longer floating. The microcontroller is going to read a high when the switch is open and a low when the switch is closed. This microcontroller just has an option of adding that same functionality internally. But since we're trying to turn an LED on and off here, we're going to set that pin as an output. Same as before, we'll have output in all caps. Now when we program the board, the LED is lit up with the same brightness as the power pin. And we can turn the LED off by writing low instead of high. Now we know that we can turn that LED on and off when we want to. I'm going to connect a push button and then read the state of that push button in code and have this turn the LED on and off. Since the Arduino Nano has selectable pull-up resistors, I'm connecting this switch between pin D12 and ground. And then in code, I'm going to do a digital write of pin D12 to high to enable that pull-up resistor, and I'm going to make sure that it's an input. And then for the main loop, I'm going to repeatedly check the state of that pin using something called an if statement. To check the state of the pin, I'll do digital read of pin 12. And then I'll do a double equals because that's sort of what you and I think of as what equals means. And if the pin is low, I know that that push button is being pressed since we connected the push button between that input pin and ground. So what I'm going to do is make the LED go high. And then the other half of the if statement is an else statement. So basically what this is saying is if whatever happens in the if statement is false, we're going to execute the code that's in here instead of executing the code that's in here. So for this I'll do digital write 13 to low. Now let's see what happens when we program this. Programming this doesn't yield the behavior that we're really expecting. Even though it's not really easy to see from this camera angle, that pin is glowing even when I'm not pushing this button. And when I do push the button, it just glows a little bit brighter. So what's going on? Back in the code, which we'll remember executes from top to bottom, we're setting pin mode to an input after we're doing this digital write. Now, these digital write, pin mode commands like that are part of libraries. They're actually a lot of instructions that get called when you call like a digital write or call like a pin mode. And what's happening is when we set this pin mode to input, it's overriding what we have here like it never even existed. So to fix that, I'm going to set the state of the pin after I set the mode of the pin. Now when we program it, the LED is off when the push button is off, and pressing the push button lights the LED. The next part is making the delay. That's actually one of the easier parts. To make a delay, we'll use a function that's built into the Arduino library called delay. And then inside the delay, put the number of milliseconds we want the delay to be. So for us, let's do 1,000 milliseconds or 1 second. As you can see, this works like expected, but we're not quite out of the woods yet. When we press this switch and we see the LED light up, it's easy to assume that we're going from a state that's off to a state that's on, but that's not actually what's happening. Microcontrollers see things a lot faster than we do. Depending on the speed of the microcontroller, this loop can be executed thousands, millions of times a second. And when we push that switch, the contacts are doing this. The noise that occurs when a state changes between, for instance, high to low or low to high, is known as bounce. And it comes from what the switch contacts actually do. But in our application, a bigger concern is induced EMF. When we've got something that's generating a giant magnetic field and then that magnetic field collapses, the lines that we use for our switch are going to see something that looks similar to a bounce. They're going to see voltage go in one direction or the other, try to clamp against a rail, and then put in a spike that can re-trigger our circuit. And if we're trying to turn something off and on accurately, this can be a real problem. It can even lead to a state where we never actually shut off our inductive heater. Now, a microcontroller can only see zeros and ones. So this is what that noise looked like to a microcontroller. We're going to sample here, get a 0, 0, 1, 0, 0, 1, 1, 1, 1. Now, if the microcontroller is even faster than that, it might look like this. But regardless of how it looks to the microcontroller, there's a pretty easy trick that we can do to debounce it, to get a clean signal. And that trick is to count the number of pulses in a row that we're getting that have the same value. The first time this pin switches states, that count of the number of same pulses in a row is going to be 0 because it just changed. There's nothing in a row. And then as we count the pulses, this number of pulses in a row increments. So here we're at 3, but when this changes back to 0, the count goes back to 0. Then it starts counting at 0. Here's a change, it goes back to 0. And then here we start to get a lot of pulses in a row. Since we only care about when the pin is really low, we can implement this in code pretty simply. We'll start out by declaring a variable, an integer variable, and we'll call that variable debounce. And then inside the loop, when that pin reads as a low, we're going to count how many times in a row that pin reads as a low before we actually consider it to be low. We'll do that by incrementing the debounce variable every time that pin is read as low. And then if it's ever not read as low, we're going to reset that debounce variable. And then we'll only execute the code that we want to execute when that debounce variable is greater than a certain number. In our case, we'll pick something like 1,000. When I have the debounce variable set to 1,000, pushing this button is still going to activate our 1-second delay. It doesn't really look any different to me than it did before, so I'm going to wonder whether or not this works. What I'm going to do is I'm going to start to increase the size of it. So I'll try 10,000. And what I'm going to expect is that when I go to use this, eventually I'm going to see some delay between when I push the button and when that light actually comes on. At 10,000, this thing still lights up pretty much when I push the button. So I'm going to try increasing it to maybe 100,000, see how that works. But when I increase it to 100,000, the button presses don't even do anything. Why is that? Every variable has a size that's associated with it. Up here we called this an int. And in the Arduino, the maximum size this can be is 32,767. Since we're comparing a number that can never go beyond 32,768 to 100,000, we're never going to actually see anything unless we change this from an int to a larger number. In the Arduino platform, there's a number known as a long, and a long can hold about 2 billion. So this code should work. And when we test it out, we can see a noticeable delay in between pressing the button and actually having this light up. Now, the optimal size of a debounce variable depends a lot on what signal you're trying to measure and what type of noise you're going to encounter. But for us, 1,000 is fine. At least now we know that the code works. But there is one more condition that we haven't handled yet. If this debounced variable goes over 1,000 and we start executing this code, we're going to need to actually reset the debounced variable right inside that loop. If this variable is not reset after we've got a debounced switch signal, what can happen is right when we end this loop, we're going to go right back to the top and come in, and we can re-enter this loop if we've got noise on the switch signal at that point. And since what we're doing is casting out that big magnetic EMF spike right when we change the state, this is important to add in. So the last thing I'm going to do on this section is connect up a relay module. This isn't actually even required for the induction heater build, but it does make showing how to connect the motor control board more intuitive, because this relay turns in that little signal that we're going to pull off of D13 into a switch, into something that's not actually attached to anything referenced to the Arduino. All that I'm really going to be doing is connecting the DC plus to 5 volts, the DC minus to ground, and the input to the D13, and then these outputs are going to act just like a push button switch. They're going to go on when we tell it to go on and turn off when we tell it to turn off. So now we've got the basic setup. Pushing this button is going to light that relay up for about a second.